few days ago, I posted an introductory video to my forthcoming book on this new realist interpretation of quantum mechanics, the Zitterbewegung interpretation. I would recommend you do not watch this video if you haven't watched the previous one, because this video is going to be far more technical. We'll really go into the nitty-gritty of it all, and we'll discuss like some paradoxes in the interpretation and really sort of the more technical stuff. Let me remind you perhaps of the basics. This interpretation addresses some series weakness in traditional quantum electrodynamics. We think quantum electrodynamics, the way quantum mechanics is being taught, is basically a theory without it's a theory about electrons and photons and their interactions, but they don't have really like a model of what an electron and a photon actually are. So the Zitterbewegung model is basically an electron model, but we can add an interpretation of what atomic orbitals then actually are, and we will also add a photon model. But let's first introduce the electron model once again. At the center there we have that quote from Paul Dirac. So Zitterbewegung is a term which actually was coined by Schrödinger, the founding father of the wave mechanical approach to quantum mechanics. He was Austrian, so he spoke German, and Zitterbewegung is German. So German was an important scientific language then, as important or even more so than English. So Zitterbewegung means trembling or shaking, and Schrödinger found this Zitterbewegung as sort of a trivial solution really to Dirac's wave equation for an electron. And this is how Dirac describes it in his Nobel Prize lecture for physics. Nobel Prize he got with Schrödinger. Actually, Dirac and Schrödinger shared that 1933 Nobel Prize. So he says it as follows: it is found that an electron, which seems to us to be moving slowly, must actually have a very high frequency oscillatory motion of small amplitude superposed on the regular motion which appears to us. As a result of this oscillatory motion, the velocity of the electron at any time equals the velocity of light. Now, our model, or let's say our particular flavor of this model, combines actually three equations. The first one is Einstein's mass-energy equivalence relation. That one, E is a mc squared. It's a deep equation, and the nice thing about this Zitterbewegung interpretation is that it actually offers a sort of intuitive explanation for that equation. We combine it with the idea of a two-dimensional oscillation. As you can see, we have like two linear oscillations in a 90-degree angle, 90 degrees out of phase, a sine and a cosine, and so we can add their energies and the motion because sine and a cosine, if you superpose those two linear motions, they'll drive a point-like charge, we think, in that orbit. It's just a charge. That's the nice thing about the Zitterbewegung interpretation of quantum mechanics of an electron, really, is that it sort of combines that wave-like and particle-like description that we need. The electron it's a hybrid description. Actually, we have a point-like charge with no mechanical mass going around and around, and the mass of the whole electron is really the equivalent mass of the energy of the oscillation. So that green dot there moves at the speed of light. So the velocity v is actually equal to c. But those formulas apply. The velocity c is going to be equal to the radius of the oscillation a and the angular frequency. And for that point-like charge, we can actually also have a momentum formula. The definition basically is just the mass times the velocity. So in this case, it's the mass times the velocity of light. So we have that oscillation. The energy in an oscillation is always going to be proportional to the square of the amplitude of the oscillation. So that's the a squared there. and it's going to be proportional to the square also of the frequency, so omega square. And then the question is, what is the proportionality constant? And that's sort of the what we do there. We boldly say that that proportionality constant is m, is the mass. So that's the E as mc square is then, the product also of the mass times the squared radius times the squared frequency. And to equate those two equations, the condition really is indeed that the velocity, the tangential velocity, is c, and yeah, that proportionality constant is effectively m. So that's sort of the first two equations there, two or three equations, and then on the right hand side we have the Planck-Einstein relation, which we write a bit differently. Usually you'll see the energy is Planck's constant times the frequency, or h bar times the angular frequency. Now the frequency, if there's a frequency, there's an oscillation again, and so if there's an oscillation, there's a cycle time, and the cycle time is always, is just the inverse of the frequency. If you have 10 oscillations per second, then your cycle time will be 1/10 of a second. So we prefer to write the Planck-Einstein relation as the energy times the cycle time, t, is Planck's constant. That sort of really models an elementary cycle. So h is really the way we interpret Planck's quantum of action here, is that it sort of represents an elementary cycle. And you can see below there, sort of to keep that that charge in its orbit, there is a force. So if there's a force over some distance, then there is an energy. So the force times the distance, the circumference, is going to be the energy. And if we multiply that with the cycle time, we have h, Planck's quantum of action. We can also write Planck's quantum of action as the product of some momentum times a wavelength. But we'll come back to that. That's the Broglie equation. So there's two views really. A Planck's quantum is a force times a distance times a time, a cycle time, and so a force times over a distance, that's energy. If we have a force multiplied by some time interval, then we have momentum, and then we can multiply it with a distance and we get h. So Planck's quantum, we can really see it in three different ways: the product of energy and time, the product of some momentum and the distance and the loop, and just for what it is, a force times a distance times some time. So yes, that's Planck's the Planck-Einstein relation, basically, a formula for Planck's quantum of action. So if we combine it all, then we get what we have in that at the bottom there. E is mc square is m times a square times omega square, and then we substitute for the Planck-Einstein relation, and out of that formula then we can get the radius formula for the radius, and it's h bar divided by m times c, which is the Compton radius, and I'll explain what it is in a moment. I always say Compton, but he was actually an American physicist, so I should say Compton. But well, Compton. He came from France, I guess, his family. So so what Dirac said indeed is, that there's a really small amplitude. The Compton radius is, 386 picometer. So that's exceedingly small, and that's why we cannot really observe that that oscillation. And also, indeed, the frequency I calculated there at the bottom. It's the frequency is, well, the Planck-Einstein relation tells us that it's the energy divided by Planck's constant. So the energy of our electron expressed in Joule is about 8 times 10 to the power minus 14 Joule. The Joule is a pretty big energy unit. That's why we usually express energy in electron volts, smaller unit. But here we're just using our SI unit. So we divide it by Planck's quantum of action, Planck's constant, and we get 0.123 times 10 to the power 21 hertz, 10 to the power 21 oscillations per second. That's enormous. That's sort of way beyond the frequency of the hardest gamma rays. So that's a frequency that is effectively non-observable. We're here with the Quantum scattering. I just wanted to show sort of what it is, and so how we can think of that Compton scattering radius. So Compton scattering occurs actually with fairly high energy photons, X-rays basically, and they'll really they'll mess with an electron. They'll interfere. The electron, the idea is actually that it sort of absorbs them basically, and then it sort of emits a photon with a slightly different frequency, a bit of a lower frequency. So the electron will return to its equilibrium position after absorbing some energy and then ejecting it in the form of a photon, and the energy difference between the incoming photon and what leaves again is it translates into kinetic energy. The electron's kinetic energy will change, it will recoil. We have two angles there, phi and that the other angle there. So the delta angle. We have a formula for that delta angle. You've probably done a course, a basic course on quantum mechanics, so you can find a proof for that formula in those courses. Professor Zwiebach, for instance, if you've done that MIT EDX course, which I really recommend, he really gives a very great and simple proof for that formula. So that's Quantum scattering, and it's different from low energy photons that sort of also engage with an electron. That happens too, but we have a different scattering radius than a much smaller one, the Thomson radius, the classical electron radius, and that's really where the photon is just going to sort of bounce off. We have two billiard balls, but the electron is like the really big billiard ball, and the photon is really small. But there is a bit of an exchange there, and a bouncing off, and but it's sort of the photon is not gonna change frequency, and there's no messing around, I would say, between the two when you have Thomson scattering. So at the bottom there, I add a formula because I didn't do that on the previous slide. It's sort of expressing Planck's quantum of action in terms of the product of momentum and the wavelength. We can only do that for waves or an oscillation that moves at the speed of light. So the formula is really valid only for something that's traveling at the speed of light. We will have two different things traveling at the speed of light in our particular flavor of the Zitterbewegung interpretation of quantum mechanics. We have that point-like charge in the electron, so there's no mechanical mass there. It's really that toroidal photon, as Burinsky calls it, which goes round and round at the speed of light. But we will also have the photon. The photon has no charge. It's just an electromagnetic oscillation. We'll be very precise about what it is exactly in 10 or 15 slides from now. So the real electron, well, we also have an electron, of course, in a nucleus. Free electrons are fine, but usually you'll find an electron in an orbit around a nucleus, or traveling between nuclei, or in a molecular orbital or something. And that's a weirder animal. We'll also make sense of that, but that's gonna be the third model. So yeah, that's basically it. I talked about Quantum scattering and Thomson scattering, and that's sort of what we need to think about. So there's various views of this thing. I think of them as being complementary to each other. We have Hestenes here. Hestenes is sort of David Hestenes, an American physicist who revived that whole Zitterbewegung interpretation in the 1980s. His interpretation of the Zitterbewegung is really that of a current ring, literally a perpetual loop of electric current. I show here that it's that idea is not weird. It naturally occurs in zero resistance conductors. The illustration is from an illustration on perpetual currents in the context of superconductivity. Well, when you have a magnetic field, the B0 field in the left-hand side of the illustration, and it goes through a ring made of superconducting material, we can then cool that ring below the critical temperature and then switch off the field. Lenz's law, so that's just, Faraday's law of induction, basically. It tells us the change in the magnetic field will then induce an electromotive force. So that's what we get on the right-hand side, and B there. We get an induced electric current. Direction and the magnitude of that current will be such that the magnetic flux it's generating will compensate for the flux change due to, a switching of that field, the change in the applied field. Sounds a bit complicated, but it's really a logical consequence of Maxwell's equation. So Heston has summarized his Zitterbewegung interpretation of an electron like this. He said, the electron is nature's most fundamental superconducting current loop. Electron spin designates the orientation of the loop in space. It's up or down. And the current goes in this direction or that direction. The electron loop is a superconducting LC circuit. The mass of the electron is the energy and the electron's electromagnetic field. Half of it is going to be magnetic potential energy, and the rest is kinetic. He probably means, that electromotive force over the distance over the current loop. So electric energy. The idea here is sort of that point-like charge really that's going around and around. That's just a charge. It's an electric charge, and electric charge only. That's very important. It has no mechanical mass or zero rest mass, you could say, if you prefer that expression. So that's why its velocity will equal the speed of light. Now again, a point like does not necessarily mean it's got no dimension whatsoever. Besides the Quantum radius, we have that Thomson radius, so that's a much smaller scale. And as I said, that also comes out of photon scattering experiments. But there's no interaction, no absorption and re-emission, no interference, so to speak. The photon just bounces off. But that's sort of where, this ring here has some diameter, and you may wanna think that of the same thing in our model. The Compton radius and the Thomson radius are related one to another through the fine structure constant. We talked about that already. The Compton radius is the Compton radius is the relevant scale for Compton scattering, inelastic scattering. The Thomson radius is the fine structure constant times the Compton radius, alpha. Alpha, the fine structure constant, is equal to 1 divided by 137, more or less. It's 1 divided by 137 is about 0.0073. So that's less than a percent. It's like a scaling constant. We'll come back to that. So yes, that's sort of a nice picture we have. A mental picture which we can work with. And but let's look at the problems with this model a little bit. This is what Alexander Burinsky, he's a very eminent Russian scientist, about the same age as Heston is now, 85, but he sort of still publishes and writes a lot. So he wrote me the following when on Heston's interpretation, basically, or the Zitterbewegung interpretation. I know many people who consider the electron as a toroidal photon, so that's the point-like charge, and do it up to now. I also started from this model in about 1969, that's the year I was born. And he published an article in that's a Russian journal in 1974 on it, Microgeons with Spin. Editor Lifshitz prohibited me then to write there about Zitterbewegung. I'm not sure why, but I understand there must be some ideological reason. There's a remnant on this notion, and but there was also this key problem, and that sort of that sums it all up. What keeps that point-like charge in its circular orbit? Because a current in a superconducting ring is a current in a superconducting ring. It's made of a superconducting material, and in free space, the point-like charge is just, it should just spin away. There's indeed a force needed to keep it in its orbit. So that's actually where I prefer to think of the Zitterbewegung really as a two-dimensional oscillation. It's really one of the key innovations, one of the key ideas in my book. So yeah, you can see a bit here. We have the elementary wave function there, Euler's function. We can just add a coefficient a to sort of increase or decrease the radius. Here we just have the unit circle. But yeah, you can see that the angle, the argument of the wave function, it goes round and round, and basically it's the superposition really of a sine and a cosine that gives us Euler's function. So we should so the mathematical description here really fits the model, the electron model, that point-like charge orbiting around. So let me talk about that idea of an oscillation in two dimensions, really. The non-relativistic analysis is, I have a metaphor there at the bottom, two pistons, two cylinders in a 90-degree angle, indeed, linear oscillations, 90 degrees out of phase, and also in a 90-degree angle, one to another. So one will follow the sine, and the other will be a cosine function. And we can calculate kinetic energy as we usually do, and potential energy for those oscillators. For one oscillator, the kinetic energy is going to be, mv squared divided by 2. So this is a non-relativistic analysis. And we get there, if you write it all out, that formula. Delta is just, your starting point. And then you have the argument, omega times t, the angular frequency times time. So if we add the potential and kinetic energy, you know how it goes really. Both vary. When the mass on a spring, or the mass in that cylinder there, passes the 0 point, then the velocity will be will reach a maximum point, and the potential energy will be 0 though, because the spring is at its 0 point. So, but at all times, if you look at that graph, the sum of the kinetic and potential energy is a constant, and we can calculate it. It's the product of the mass times, the square of the amplitude of the oscillation, and times the square of the frequency divided by 2. And so, if we have two independent oscillators, say that 90-degree angle there, then we can just add the energies, and we get that formula that we started with. We can write it really as sort of, the ratio of the energy and the mass is a constant. It's c squared. It's and c squared we can equate it with a squared times the frequency squared, and that's the grand idea. And then indeed the Planck-Einstein relation gives us that radius. So, but that's a non-relativistic analysis. We should actually because we said that point-like charge has no mechanical mass, it really goes around at the speed of light, and that's where we need a relativistic analysis. So the relativistically correct force equation for one oscillator is, well, it looks the same. So the spring has sort of that spring constant, the k, and the force that's going to cause the change in the momentum is going to be the negative of that linear force. The force changes with the extension or the compression of the spring, minus kx, that's the force, and Newton's law tells us it's going to cause that change in momentum. Time derivative of p should be equal to that force. So, but the relativistically correct formula for p is a mass that depends on the velocity. So that's why we write mv times the velocity, and mv is the Lorentz factor there, gamma, times the rest mass, m0. So it varies with speed, because gamma varies with speed. So you have the formula there, and we write out that Lorentz factor. I write it also as 1 over the square root of 1 minus beta squared. Beta is the relative velocity, the ratio of v and c. And I also write it as dt over d tau. Tau is the proper time, because you shouldn't worry about it, but we don't need it. But I just wanted to remind you that we no longer have a unique concept of time in a relativistic analysis. There's the time in our reference frame, which is t, which we know as the coordinate time, and then there's the time in the reference frame of the object itself, tau, sort of the proper time of our electron. We may want to use these two concepts of time in a later development, so it's good to introduce them here. But so let's get on with that equation above. It's a very simple differential equation. When you first learned about an equation like this, no one probably told you it's a proper differential equation. But as simple as it is, we're still not going to solve it really, because we don't have to. We will just derive an energy conservation equation from it. We do that by multiplying both sides of that f is dp over dt equation with v is dx over dt, and then, well, we can bring some factors inside of the operator, the derivative, and then rearrange a little bit, and you can do it. You just go through it for yourself, and then you've got that energy conservation equation, that the derivative of the energy with respect to time, d over dt, is the derivative of that expression between the square brackets. 1 over 2 times k times x squared plus the relativistic mass times c squared. And so that derivative is 0 always, regardless of the value of x and regardless of the value of v or mv. So that sum of two terms inside, that's a constant. So the two terms vary, but it's like, the 1 over 2k x squared, we recognize that again as sort of, the potential energy. It depends on the position of the spring, the position of the mass. And then the other term there is, a relativistically correct formula, I would say, for the kinetic energy. So we can set, we know that if x is 0, then potential energy will be 0, but the other term will then be equal to the total energy of the thing. And I said when the potential energy is 0, then the kinetic energy is going to be reach a maximum. And so in our model we really do think that sort of when it goes through the center, the velocity, it is the speed of light. So we have that mc times c squared. That's where the velocity is equal to c, and so that's the energy in that relativistic oscillator. So the interpretation becomes a bit weirder. To be honest, I'm puzzled by it. So I won't add too many comments here, because we go from, like, in a non-relativistic analysis we have that idea of two perpendicular oscillations. Here we've got like one only, but the idea of a frictionless oscillation is still there. So we got a sort of perpetual mobile, or whatever you want to call it, and that's really the point to note. Okay, this is a very dense slide. The big advantage of the Zitterbewegung model is really that it's all very precise. We can really calculate everything. When I mean everything, I mean everything. See what we get here. We have that model there, the point like charge. There's a force on it, and we have the energy. It's the energy of the equivalent energy of the rest mass of our electron in that hybrid description. So the force is the force times the distance times the loop. Circumference is the energy, so we can calculate the force. We get this result. It's 3.37 something hundredths of a Newton. That's big. That's huge, because the scale is really so small. This force is equivalent to a force that gives a mass of 33.7 grams, an acceleration of 1 meter per second. That's just the definition of, a Newton. And that's huge. Because I said, yeah, we're talking the content radius here, so picometer scale. So that's enormous. We'll say a few things about that in a moment. We can also calculate the current. We have the the charge of our electron, and we have a frequency. So the current is the frequency times that current that goes around and around. So we use the Planck-Einstein relation, and we have all the calculations there. The charge of the electron, then the frequency that we calculate, which was that enormous number, 10 to the power 21. And we get a household level current, almost 2 amperes. That's huge, a household level current, again, at that, very, very, very small scale. So there's another calculation we can do here. We know that force is it grabs onto a charge. It's got nothing else to grab onto. It's not a gravitational thing. It's sort of because there's no rest mass. That point-like charge has no mechanical mass. So the force is really electromagnetic. It grabs onto a force. So we can write it as the product of the unit charge and some electric field. And the unit charge, the charge of our electron. And so we have E there. E is not the energy here. It's really the electric field. And because that force is so humongous and the charge is really tiny, we get a huge field strength. We calculated it there. The force, 3.3 something times hundreds of a Newton, and then the elementary charge 1.6 times 10 to the power minus 19 Coulomb, and so we get 0.21 times 10 to the power 18 Newton per Coulomb. That's an enormous field strength. We have accelerators that accelerate electrons. They reach field strengths of the order of 10 to the power 9. That's so 1 gigavolt per meter. That's the alternative physical dimension. So that field strength is huge. We can't reproduce it in not even in the most powerful man-made accelerators. I do an effort here also to calculate, to do, the energy density. That formula makes sense or might not make sense. It's just like a quick formula that I'm writing down and then seeing what I'm get to see if it all makes sense. And yeah, we get an enormous energy density, 0.63 times 10 to the power 24 Joule over per cube meter, or Newton per square meter, if you want to. So this amounts to an equivalent mass density of about 7 kilogram per cubic millimeter. These are amazing figures. It makes one thing. Does it make sense? I mean, with these energy mass densities and with these forces, the whole thing is maybe just, are we trying to model a black hole or something? Because we should think about the implications on this in terms of general relativity theory. How sort of is space-time being bent by this enormous mass density? Fortunately, I don't have a real answer to that, but fortunately, it's sort of like we're still way above the Schwarzschild radius. If we would calculate, if we would pack all of the mass of an electron into a black hole, then its Schwarzschild radius would be equal to what you see below there, 10 to the minus 57 meters. So that's just way smaller than the picometer scale that we got. So yeah, enormous values for the force and the current and the energy density, but still within sort of an acceptable scale, I'd say. So let's move on. Okay, here we're sort of thinking of our relativistic analysis again. That energy conservation equation, the energy formula. So yeah, what's MC? I said it's kind of the interpretation in terms of a an oscillation is not all that straightforward. What is that MC really? We know that the energy is going to be the mass of our electron, the rest mass of our electron times c squared, but it's also going to be equal to that MC. So how is the mass really spread? There's an interesting thing here because I said the interpretation of Planck's quantum of action as the elementary cycle that's involved here is pretty straightforward. We have that force times the circumference of the loop times the cycle time. We get h. So our oscillation packs Planck's quantum of action, and we'll have other cycles. We can count cycles. That's the idea. 1, 2, 3. So 1h, 2h, 3h. We'll do that when we get to the electron orbitals, because there we will really count them, and we don't count half a cycle. Half a cycle doesn't make sense. But so that's fine. We've got a pretty straightforward interpretation here of Planck's constant. But the angular momentum, that's sort of the other side of the coin. There, I mean, we can calculate angular momentum in a number of ways, but one of them is really the one I want to use here, where we talk about some mass density, and so we want to calculate the moment of inertia, and that's a mass times the radius of the rotation squared, m times a squared, and then we have a form factor. See, that depends really on your assumption on how the mass is sort of spread over your shape. If it's a hoop about some symmetry axis, the form factor is just going to be 1. If it's a disk, and we're thinking of a bit of a disk or a solid cylinder, then the form factor is 1/2. Now the thing is, we know that electrons are spin 1/2 particles, so their angular momentum is 1.5 times h bar. So the only way we find that result is by introducing that 1/2, that form factor. So again, that's why I sort of prefer an oscillator model, because it explains that there is something there, and the mass is spread out. The oscillation is not here, not there. It's a bit over. It's spread out over that radius, over that disk, and that's where that 1/2 factor then makes sense. We'll have other examples, but the current ring is sort of it's a bit more difficult. We can say that the magnetic energy is maybe spread over everywhere, but then the toroidal photon, the point-like charge, that sort of resides only in that loop then, and so it's a bit more difficult to think about the form factor with the current loop interpretation. So yeah, this is a summary of the model. So we have that spin-only electron, as I call it. It's not an orbital electron. It's really an electron in free space. The amount of physical action that we associate with is h, Planck's quantum of action. So it packs a cycle, and the energy is just the MC squared formula, the rest mass of the electron. We have the radius of that thing is the Canton radius, velocity of our photon-like electron, I would say the point-like charge is c. That's important because we'll see with the orbital electron we talk like the slow motion that we're used to, which is just a fraction of the speed of light. The frequency is given by the Planck-Einstein relation, and also by the that ratio there, the velocity c divided by the radius of the oscillation. We have an angular momentum that makes sense because it's a spin 1/2 particle. We can calculate a magnetic moment. The E is the current then, not we, and for the angular momentum the I is the moment of inertia, but when we calculate the magnetic moment, we need the current I, so times P times the radius squared, and you can calculate that, and you get that sensible value, and you have a G ratio for spin-only electron that is the theoretical value we would get from classical, from the usual QED, except that here we're calculating it. It's not sort of this weird intrinsic property of an equally weird electron that we actually, here we have a proper model, and we calculate all these things. So I have some diagrams on the right hand side, a few illustrations that I've added to sort of see, there's much more sophisticated versions of this interpretation. We have that in the red there, Alexander Berinsky's electron model. I spoke about him. He sort of really combines gravity and electromagnetic theory to sort of come up with a disk-like structure as well. But it's not a perfect disk. It's sort of slightly asymmetric, and he can play with parameters, and that's really nice. So he can play with the shape, and as I explained in the other presentation, that's really necessary if we want to use this model to explain the anomalous magnetic moment in sort of a classical fashion. So I've also added another illustration that at the bottom there, that's the idealized motion of that point-like charge. As it starts moving linearly, we get a new wavelength here. I mean, a sort of wavelength. There's this distance between two successive loops, lambda. And yeah, we have a formula for that. I'll come back to that. And then in the right-hand corner, the top right-hand corner, I've added an illustration you've probably seen elsewhere. It shows, I wanted to show this, a point-like charge in an orbit is going to precess in a magnetic field. You have the magnetic field there, B, and then you see that the angular momentum, J. But because of the precession movement, there's going to be precession. The plane of the oscillation is going to wobble about, and we really have a sort of a classical coupling then between the spin only momentum and the orbital momentum, and that's interesting because that classical coupling should explain why we don't find exactly 2 as for the G ratio, or we don't find exactly 1 like for an orbital electron. We have precession there, and classical coupling, and sort of that opens all kinds of new possibilities. So that's a very important idea, that the plane of oscillation doesn't have to be stable. That picture at the bottom there is really very idealized. It probably will wobble about. In fact, we think it wobbles about all of the time. So the plane of oscillation is most probably not really perpendicular to the direction of motion, that linear motion. Because, I mean, you've heard about Stern-Gerlach apparatus. You send an electron through a magnetic field, and you're going to measure the angular momentum, and it's always going to be like, up or down. So the plane of oscillation in that case is, you should think of it as being some, parallel to the direction of motion, kind of flat. And wobbling about, of course, because the precession is there. But that stuff you can think about for yourself, and you should. This is the interesting thing of the book, I think, that we sort of give you a lot of material and stuff to play with. So let's look at that linear motion, though. I said it's idealized out of that plane of oscillation being perpendicular to the linear motion that we're going to introduce now. And I said in an electron around some positively charged nucleus, its velocity is not going to be relativistic. It's going to be rather a fraction of the speed of light. To be precise, it's of the order, it's less than 1% of the speed of light. So we don't need relativity theory for that, but you do want to push the model and see what you get when that linear motion becomes the dominant motion. What happens there is really that the point-like charge, it always has to move at the speed of light, but if it acquires some linear motion, that means part of its velocity is sort of linear, and that's where the radius of the oscillation, it's a funny but pretty straightforward result. It needs to become smaller, and that's what you see here. You have that black and blue, and the red one, you have these Zitterbewegung trajectories for different electron speeds for a V over C ratio that is equal to 0, 0.43, 0.86, 0.98 for the red thing. And what happens here is really funny. The the circumference of that oscillation becomes a sort of a wavelength in the process. It's a really important point. We can calculate that wavelength. I write it there. The lambda is, it's the linear velocity times, well, the cycle time. You can see that, you go from one loop to the next successive loop, and then, that's the linear velocity, and, you just need to multiply that with the time. That's the cycle time. That's the time that is, the particle is going to travel at that linear velocity v. And so cycle time is the inverse of the frequency, and there you go. And so you arrive basically at this result that that linear wavelength, if I may call it that way, is a fraction of the Compton wavelength, the circumference of that oscillation. And what fraction? Well, it's equal to beta, the ratio of that linear velocity and the speed of light. So yeah, if it really moves at the speed of light, then beta becomes 1, and I said the circumference really becomes like a wavelength. So that's a strange curve, but it is what it is. And I said we don't necessarily need to think of that plane of oscillation being perpendicular to the we can make a more general analysis, but yeah, to sort of do the calculations, this does the job. So we've actually have 3 lengths in this model. That's basically the idea, and it's again to sort of come up with a classical explanation for the anomalous magnetic moment. We have the de Broglie wavelength, which is defined by the Broglie relation, right? H divided by p. But then we also have that distance between the successive loops, and then we have the Compton wavelength. So we can relate these 3, and the formulas become really interesting and easy when we use natural units. So we choose our time and distance and mass of force units such that h is 1 and c is 1. Then the Compton wavelength becomes the inverse of the mass, and the distance between 2 successive loops is, well, again, the inverse of the mass, but multiplied by the relative velocity, beta, a ratio between 0 and 1. And then we have that formula there where the Broglie wavelength times that distance between 2 successive loops, that linear wavelength is actually the square of the Compton radius. So these 3 lengths are not independent, and they shouldn't be. The whole thing is actually that formula at the bottom, the Broglie wavelength, lambda L times lambda is the square of the Compton wavelength. That's the latus rectum formula of an ellipsoid. You can see that on the bottom there on the right hand side, and I gave these ellipsoids also there. So we've got an asymmetric shape. That's the basic idea. We don't have a perfect disk. We don't have a perfect sphere. We have something in between, an ellipsoid, and that's sort of where yeah, we do believe this model gives an alternative explanation for the anomalous magnetic moment. Why is that important? Well, we know the explanation of the anomalous magnetic moment that we get out of quantum field theory, that really weird theory. All the weirdness is really in the description of the field there, and we've got these Feynman diagrams and loops, and so it's referred to as the high precision test of that kind of quantum mechanics, of that mathematical model. And there's an empirical value. There's a Penning trap. It's a wonderful mechanical device. It captures an electron in an electromagnetic field. Now its motion is really complicated. It's the superposition of 3 or 4 motions because of these electric and magnetic fields in the trap. And so, but we do get an empirical value, and the theoretical predictions of the value that we get out of mainstream quantum theory using these 3 or 4 looped Feynman diagrams and renormalization and what have you, they match that empirical value. And so there's been like a sort of a campaign to refine these measurements and also the theoretical calculations by using 4 loop diagrams instead of 3 loop diagrams. And it's been going on for decades. And somebody called it like sort of a tennis match between experiment and theory, and it's like a game without end. And that's sort of where we wonder, is there another game in town? We think there is. It's really this classical explanation based on classical couplings between various motions that are superposed on each other, and on the based on the Zitterbewegung interpretation of what an electron might actually be. So this is a testable prediction of our model. It's the litmus test of the model. If we can show that so-called anomalous magnetic moment is not anomalous at all, then our interpretation wins. So Alexander Burinsky is actually really working hard on this. He already has a first-order approximation, which actually explains 99.85% of the anomalous magnetic moment already. It's Schrodinger's factor, the fine structure constant, divided by 2 pi. So we only need to find an explanation for the remaining 0.15% of the anomaly, and I think that 0.15% must be some relativistic effect, or as I said, this classical coupling between the various layers of motions. As I said, a real electron is not a spin-only electron, it's not an orbital electron only, and so those G ratios, 1 or 2, it's going to be something in between. But I don't want to dwell on that here. I did that in the first video, and we should move on, because I see we are approaching an hour and we're only halfway. This is going to be a quite a long presentation. Yeah, let me just repeat again that the whole model gives us sort of like, the fine structure constant pops up everywhere, and it gives us a pretty natural explanation of what it actually is. It is a bit of a scaling constant. It relates velocities, it relates radii. As you see here, the Thomson radius is alpha times the Compton radius. So, and the Compton radius in turn is, alpha times the Bohr radius. So the Thomson radius is alpha squared times the Bohr radius. So I calculated it there. It's at a picometer scale, also not 386 picometer, but 2.818. So that's the Compton radius divided by 137, because the fine structure constant is 1 divided by 137, about 0.007 something. So we have the formula for the classical electron radius, the Thomson radius. You see that there. It's the square of the electron charge. Well, E square is that special electron charge. We have it in Coulomb divided by 4p times the electric constant. You see that there. I write out various formulas. You can look at your ease. It's basically a formula for the fine structure constant. That's the ratio of the classical electron radius and the Compton radius. And so we get that formula for the fine structure constant. The thing I want to draw attention to is that E squared is we can write it as the product of the electron, the classical electron radius, and an energy mc squared. That's really interesting, because that's a formula we get also when we apply the de Broglie relation to a photon. That's the other formula you have there. H is momentum times a wavelength, and we get this formula, the energy times a wavelength is h times c. So we have something, Joule physical dimension is the same, and energy expressed in joules time a wavelength expressed in meters. So that's interesting, because we can rewrite that as Newton times the square of a distance, so a force times a surface. I like these dimensional analysis, because it gives us a bit of a clue of also what an oscillation might be. Maybe we should not be thinking of a force grabbing onto a point-like charge, but more a force grabbing onto some surface. When you calculate energy densities, you also get something expressed in Newton, so force per square meter. Joule per cube meter, you can rewrite it as Newton meter divided by the cube of a meter, so that's a Newton per square meter. So I know probably you're not getting much of what I'm trying to say. I'm actually a bit thinking about these things myself. It's one of these more metaphysical points of the model that I want to further explore. Okay, we're ready actually for the next thing, the other model, and that's sort of where we talked about orbital electrons and an electron in orbit. That's a completely different model. You can see it there. We have a centripetal force there. There's no force that keeps the point-like charge in an orbit, spinning around at the velocity of light. But we know we have a slow orbiting electron, or Zitterbewegung electron, that is going around the nucleus, and so we have an force of attraction. And but the idea is really the same. We have the same elementary cycle, I would call the physical action that is associated with this cycle, where we have a much larger radius, the Bohr radius, and slow velocity. V is going to be again the radius of the oscillation a, but it's going to be the Bohr radius, not the content radius, and the velocity, is going to be alpha times c, so it's just less than 1% of the speed of light. So we have these classical formulas, non-relativistic formulas at the bottom of that illustration there, and it just shows what's going on there with centripetal force, and the electron is moving around, so there's a path of inertia, and the combination of the inertia and the centripetal force is what makes the electron go round and round. It might seem a bit outrageous to revisit the Rutherford-Bohr model. You know that in the mainstream interpretation of quantum mechanics, they'll let you study the solutions to the Schrodinger's differential equation. So, but no, here we just do the same thing. We say, angular momentum. We have that quantum mechanical rule comes in units of h bar, and yeah, we like to think of that. Physical action comes in units of h. 1h, 2h, 3h for the various orbitals, and same thing. We can calculate that angular momentum and write it as basically, very classically, the product of some momentum, something that has momentum, that electron, and the Bohr radius. And so for the first Bohr radius is going to be equal to h bar. And it's saying just the same that, that loop is going to pack, 1 unit of h in terms of physical action. So then instead of the radius, the Bohr radius, we have the Bohr wavelength, just the radius times 2 pi. So again, we have that fundamental expression for Planck's quantum, the energy times the time, and p, the momentum times the wavelength. And so we can calculate all these things again, the radius and the force that is involved and the energy, and these formulas all involve the fine structure constant. And so the values are much lower. We calculate the energy there. That's interesting actually, because for the energy we get the energy of the electron in free space is mc squared. Here the energy of that loop, the energy of that oscillation, is alpha squared times mc squared. And so alpha is the fine structure constant, so that's 1 divided by 137. And so the square of that tiny value, 0.007 something, is going to be even really, really small. We get a really small energy value. And that's fine, because we know that we'll need to calculate the energy of this loop, but also of the second orbital and the third orbital a bit further away. We'll have different velocities and different radii. And yeah, it can be a tiny energy difference, because we know that's the hydrogen spectrum, the photons that we get when an electron goes from one orbital to another. It emits a photon that is, that has a low energy. Is nothing compared to the energy that it's packed in a spin-only electron. The thing, though, what is surprising about the energy formula that we get out of our, I would say our Zitterbewegung model, but then applied to the Rutherford-Bohr atom hydrogen, it's slightly off actually. We have a 1 or 2 factor that we're actually missing. The ionization energy of hydrogen, so the energy it takes to get to ionize hydrogen, to get that electron out of its orbit, is actually indeed that formula, alpha squared mc squared, but divided by 2. And Yeah, that's another. So we need to think about the energy concepts that we're using here, and that's what I'm writing there. It's twice the kinetic energy. I have a formula there, h bar squared divided by 2ma squared. Let me explain how we get that formula, and then see how that makes. This is Feynman's explanation of the energy concepts. That's actually his model of an of the Bohr atom. He says the kinetic energy, I said the velocities are kind of low of that electron, so we have the mv squared. M is the mass of that, the rest mass of our electron, v squared, while the velocity, I said, a fraction of the speed of light, a small fraction. So we can use that formula. Now we have our formula there, the Broglie relation or the Planck-Einstein relation. Planck's quantum is the product of an energy and a cycle time, and we can also write it as the product of some momentum times a wavelength. So we get that formula there on top. The momentum is equal to h bar divided by the Bohr radius. So p squared divided by 2m, the kinetic energy is going to be equal to indeed h bar squared divided by 2 times the mass times the square of the Bohr radius. The potential energy is, we get that out of the Coulomb formula, right? It's the product of the two charges. So we get a minus sign. We have the proton and we have the electron. And while the 4p times the electric constant there is integrated in E square, it's another way of writing the unit, the elementary charge, and yeah, divided by the distance between the two, which is the Bohr radius. So the whole idea is that an electron in an orbit, a hydrogen atom, an electron around positively charged nucleus, the proton, the configuration must minimize the total energy. Total energy is the sum of the kinetic and the potential energy. See, the potential energy is negative because when we calculate potential energy, we need a 0 point. So, and the 0 point is taken as at one very, very, very far away from the nucleus. So when we bring it, the energy is going to decrease and it's going to become negative. So the variable is the Bohr radius, and so we can calculate it by calculating the minimum value for the energy. We get that by just taking the derivative of the energy with respect to the Bohr radius and equating it to 0, and then you get that radius, which is 1 over alpha times the Canton radius, about 53 times 10 to the power minus 12 meter. So yeah, now we can calculate the Rydberg energy because that's the corresponding energy, kinetic plus potential, and that's what we do there. E is h bar squared divided by 2m times the Bohr radius squared minus E squared divided by the Bohr radius, and then when you write it all out, you get that Rydberg energy, which is what we had, alpha squared times mc squared, but divided by 2, and we get the minus sign as well. Minus 13.6 electron volts, if we express it in electron volts rather than joules. So yeah, that's sort of the interpretation of that 1 over 2 factor. If we look at these energy concepts, the other thing I've been thinking though is I sometimes think it's got to do maybe with Pauli's exclusion principle, or maybe Pauli's exclusion principle. You know what it is. I think of it as a bit of an inclusion principle because it basically says, two electrons, they will want to be together in one orbit. It's like a Cooper pair in superconducting materials. They repel each other, and strongly so, but at the same time, if they have opposite spin, we'll have two electrons occupying one orbital. They can sort of reduce their energy by apparently being there in a pair. It must be something physical. Perhaps the Zitterbewegung model could explain it in terms of the orientation of that plane of oscillation. Again, I'm not sure. Perhaps the plane of oscillation is going to be perpendicular. One electron and the other are going to have two different planes of oscillation. I'm not sure here. I'm just guessing. But yeah, that 1 over 2 factor definitely is a bit of a strange metaphysical, I'd say, a characteristic of the model. But well, let's not worry too much about it. Let's go to yeah, the summary. So we have the same here as that we did the calculations that come out of our model. They're not weird properties of some weird electron that we don't understand. No, it's something going around, and this, with a cycle, and the cycle will pack H, 2H, 4, depending on the electron orbital, the first, the second, the third. So we have the energy that we can associate with each of the orbitals, depending on the key number there, n, and the radii is going to be n squared times the Bohr radius, and then the velocities, as you can see, it's sort of a fraction of the speed of light, but divided by n. So the further you move out, the slower the speed is going to be. We have the frequencies that we can calculate. We have the angular momentum formula. The angular momentum is interesting. It's sort of the corollary of that action. Sn is n times h. Well, the angular momentum, we have n times h bar, and we have a magnetic moment and a g ratio. And the g ratio is that theoretical value for the g ratio for an orbital electron. It's 1. It's not 2, like for a spin-only electron. So that all makes sense. And well, now for the Rydberg formula, we'll have a photon when that's being emitted or absorbed when an electron makes a transition. You see that at the bottom there, from ns1 to ns2, or the other way around, or from ns7 to ns5. We have all these series: the Lyman series, Balmer series, Paschen series, Brackett series. And so the photon is going to have a wavelength, and the photon is moving at the speed of light. So we have that formula. The wavelength is equal to the speed of light divided by the frequency. And we know, the frequency is given by the Planck-Einstein relation again. So it's the energy divided by h. So if we substitute, we get a formula for lambda. Lambda is hc divided by the energy. And so that's how we get the Rydberg formula, really. If we write it as 1 over lambda, the inverse of the frequency, it's going to be the difference in energy between two orbitals divided by hc. You see that there. 1 over lambda is equal to delta E, the difference of in energy between two orbitals, divided by hc, and then we can use that energy formula, and we do get the Rydberg formula out of our model. So that's nice. So we have the series. It's the gross structure of the hydrogen spectrum. We know there's magnetic effects that explain a finer structure within this gross structure. That's actually where, again, the fine structure constant pops up. That's where it gets its name from. But I haven't analyzed that yet. That's on the agenda. Okay, so here we get a bit of a feel for the model because we're calculating what happens with those radii, the velocities, the frequencies, and the cycle times as the electron moves out from the center. So you can see the velocities go down all the way to 0 in the end for n going to infinity. And the corresponding cycle time increases, and it increases actually as the cube of n. You can see that there, the angular frequency is proportional to 1 divided by the cube of n. So when the cycle time is the same thing, it increases as the cube of n. So using totally non-scientific language, we might say that the numbers suggest that the electron starts to lose interest in the nucleus as it moves out, and it sort of just gets ready to leave and wander around as a free electron. So at the bottom there again, I put the grand result. We got the Rydberg formula, the energy difference between the various orbitals. So next, so we're finally ready for the because I need to wrap up for our photon model. That's the third building block in our book. So the Bohr orbitals, as I said, they're separated by an energy, but also by an amount of action that is equal to h. The first Bohr orbital is associated with h, and the second one with 2h and 3h. So each Bohr orbital is separated by an amount of action that is equal to h. So when an electron jumps from one level to the next, let's say from the second to the first, got an excited electron, and then it comes back to the equilibrium situation, the atom will lose 1 unit of h. So our photon, and that's the funny thing here, our photon will have to pack that somehow. And it will also have to pack the related energy, which is given by that Rydberg formula. So to focus our thinking, let's consider that transition from the second to the first level, for which, well, we have that factor in the Rydberg formula, and that becomes 1 divided by 1 squared minus 1 divided by n squared, which is n is 2 squared. So we get a factor here 0.75. So the photon energy will be 0.75 times the Rydberg energy, which is about the Rydberg energy is 13.6 electron volts. So here we have a photon that 10.2 electron volt. Now the funny thing here is then if the action of that photon, the action it packs, is going to be equal to h, then we can calculate the cycle time. And it's very simple. The cycle time is given by the Planck-Einstein relation again, and the cycle time is the inverse of the frequency. So that's how we get it, and we get 0.4 times 10 to the power minus 15 seconds. So really short, and well, that's actually a wavelength. That's the wavelength of a photon of that energy of 10.2 electron volt. It's 122 nanometer. So we get a physical interpretation of the photon. The length of our photon is, the wavelength. We call this like a one cycle photon. The wave function represents the rotating field vector itself, the force field. I'm noting this because you will, like in Feynman, you will, get these weird calculations of the, the Q of an atomic oscillator, and then you get, they think of a photon as some kind of wave train, but if you do that, you get wave trains with a length of like 2 or 3 meters, incredibly long wave trains, and the photon is it is particle-like. It can't be like have a length of meters. So this model is really neat. It gives us a physical interpretation of a photon. It's just like one cycle of an electromagnetic oscillation. So here we have actually the the model. Again, we have the elementary wave function, but yet another diagram here. Here we just have indeed no point-like charge or something. We just have an electric field vector E that goes around and around, and it has two components, a horizontal one and a perpendicular one. We can write it as the electric field vector is these two components, EX and EY. So it's just a single cycle traveling through space and time. It packs 1 unit of angular momentum, h bar, or the other side of the coin. It packs 1 unit of physical action, and it really gives us an equally delightful interpretation of the Planck-Einstein relation, because we can do what we did for the electron. We can express h in two alternative ways: the product of some momentum over a distance and the product of some energy over some time, and it really corresponds the distance and time we get to the wavelength and the cycle time of our photon. And so yeah, we've got a pretty consistent picture of the photon here. The formulas, they do imply again that equation for a photon, that the energy times the wavelength is the product of Planck's quantum and the speed of light. So if we have a wavelength, it's kind of funny, but we can also sort of think like, hey, maybe we should associate some radius with the wavelength of our photon. And yeah, we can do that if we divide the wavelength by 2p, and that's sort of where I'm putting that nice diagram of Celani and Vassallo again, where we're at the other extreme when with the electron, sort of that toroidal photon or whatever you want to call it, the black thing is just there, and if things start moving linearly, then that circumference it does become a wavelength, and so we yeah, we can sort of, the wavelength, that red thing, is the wavelength of a photon. If we think at the extreme where, you know, the linear velocity is the speed of light, then we have a wavelength, but we still can sort of associate a bit of a radius. And well, I wrote a formula there again of the energy of our photon. I express it as the product of some force times a radius rather than a wavelength. And that radius is then, you know, the wavelength of our photon, you know, lambda or gamma. The gamma symbol is the symbol of a photon divided by 2p. And, you know, I get a field strength. And field strength, again, what kind of field is it? Well, it is an electromagnetic field, right? It doesn't have a charge to grab on though, but it's electromagnetic in its nature, because, you know, it comes out of a model that is electromagnetic only, where we're not talking about, you know, gravitational waves here. So we can use this formula again, because if there's a force, then, you know, there's we can express it as the field times the unit charge. And now the unit charge, well, we take the Coulomb here, not the electron charge, and we get a value for the electric field that's involved in our one cycle photon, and we get a pretty reasonable value, 84 times 10 to the power minus 12 Newton divided by Coulomb. So that's normal actually. A photon has much lower energy, and so yeah, the field and the forces that are involved are much smaller than the forces and the fields that were involved in our Zitterbewegung electron. Um, I need to wrap up, but this is a final consistency check sort of on the model. I said the energy of an oscillation will always be proportional to, you know, well, I write the amplitude and its frequency, but it's actually the square of its amplitude and the square of its frequency. So do we get a meaningful result here? So here we're gonna write that proportionality coefficient as k. E is k times a square times omega square. Now we substitute here, and let's see here. If we substitute, we insert a Planck-Einstein relation. So and then the amplitude of the oscillation, if we substitute that for the wavelength, we get a formula. The energy is equal to, you know, k, that's sort of that proportionality coefficient, times, you can see the whole thing here, but it simplifies to, you know, h square, c square, e square divided by e square times h square, simplifies to c square. So we have the energy is equal to k times c square. So the condition for that energy formula to be, you know, logically consistent with the formula we have for the energy, it's always like E is mc squared, right? So the condition we get out of that is that k is equal to m. So that proportionality coefficient, we just started out with noting that the energy is proportional to the square of the amplitude of the oscillation and the frequency. We see that for that formula to make sense, the proportionality coefficient needs to be equal to the mass of our photon. So yes, it is a consistent model. Now, what about uncertainty? I note this presentation is already like 1 hour and 20 minutes now. I'm going to be really brief about that because, yeah, everything we said so far doesn't involve uncertainty. Uncertainty in the Zitterbewegung model, you know, we'll probably need to rewrite Planck's quantum of action as, and that's really interesting. We said, you know, a force has a direction, it grabs onto something, and then, you know, distance, time. It's very tempting in this model to sort of think like, you know, when we have uncertainty in the momentum is a vector quantity. So why would Planck's quantum not have a direction? Why would we think of Planck's quantum as a vector quantity? And that's where the question then really is what's the uncertainty? Is it in the direction or is it in the magnitude of h?
So what I put at the bottom there, the related question is really like, yeah, if we have uncertainty in the momentum p, do we really have it in the magnitude of p, or in its direction only, or is it in both? So these are the questions you need to think about. And of course, we have that figure there, the idealized zeta motion when linear motion is involved with lambda, the distance between two successive loops of our point-like charge. You see that the plane of oscillation is not clearly defined there. It wobbles around. If we have that Archimedes screw, then we have a wobbling plane of oscillation, and as a result, it's really tempting to sort of make a vector quantity of h, saying that that cycle packs, yes, Planck's quantum of action, but it's a vector quantity, like angular momentum, that has a direction only. It's a polar vector. Well, it's not a polar vector; it's a pseudo vector. But that's it. And then there's all kinds of other considerations. I put something up there. If you have uncertainty in linear momentum, it gets amplified over the distance. So, but that's just something mechanical, and it explains a lot. If you have a physical model of the electron like we have here, you get a sort of a physical explanation for the uncertainty as well. And so it becomes uncertainty. It is uncertainty, but it's deterministic. Something explains the probabilities, and that's what Einstein wanted. He didn't mind, that to just say that nature is probabilistic in its nature. He just wanted a theory that explained the probabilities in some kind of reasonable way, and that's what the model does. So that's it, really. I think it was quite a tour de force. It's a complete overview of the whole theory: electrons, photons, orbits. But it's all based on one powerful principle, really: the interpretation of Planck's quantum of action as modeling a cycle, a very fundamental cycle: the cycle of a spin-only electron, the cycle of an orbital electron, the cycle of a photon. So yeah, I should do some more thinking about uncertainty, but that's for later, one thing at a time. And well, that's it. I hope you enjoyed this presentation. If you're still listening, I must assume you do, then well, thank you.